Okay, let's see if we can look at section 11.4 in its entirety in this pencast. Section 11.4 starts with two very basic theorems, 11.4.1, 11.4.2, shown here on this slide. And if we read them, part A of 11.41, if the limit as k goes to positive infinity of the terms of a series is not equal to 0, then the series diverges. Makes sense. Then part B, if the limit equals 0, then you really don't have any conclusion. The series may either converge or diverge. So 11.4.1b is really a caution not to make any conclusions if the limit is 0. However, if the limit's not 0, you're home free, then it diverges. But look at theorem 11.4.2. If the series converges, then the limit equals 0. And that's not violating either part of 11.4.1, but it's kind of an exercise in logical reasoning, which we'll look at in the next slide. But for these two theorems, take it as carved in stone. How I see them is that before you start anything, kind of like when we do direct substitution for limits as our first step way back in chapter 2, our first step in looking at convergence, or divergence, is simply to look, does the limit of the infinitieth term as k goes to positive infinity, does it equal 0? If it doesn't, you're home free. However, 9 times out of 10, it is going to equal 0, forcing you to do something more, which we'll look at in the later slides. Okay, as promised, a little logical reasoning. Now, we're just going to break out of calculus and go into a little bit of pure logic. A lot of theorems that we looked at in geometry and some in calculus were called conditionals. Conditional statements are always in the form if P, then Q. P and Q are statement variables, and theorems that are always in if then have P as your hypothesis and Q as your conclusion. So if the hypothesis is met, then the conclusion is guaranteed. If P, then Q. Interestingly enough, as a side note, biconditionals, which would be P, IFF, or if and only if, Q, are really twofers. That really gives you if P, then Q, and also if Q, then P. Both of these are true. This one is a biconditional, and the IFF stands for if and only if. But going back to our original conditional, if P, then Q, there are 4 associated statements from any given conditional, and that would be if Q, then P, if not P, then not Q, if not Q, then not P. All of these have special names. This one would be the original or the given. This one is the converse of the given. This one is the inverse of the given. And this one is the contrapositive of the given, without going into a huge exercise and introducing what's called logical reasoning truth tables, which are really fun. This is the only one that is guaranteed to be true if the original is true. So whenever you have a theorem that's stated in a conditional form, if P then Q, the only one that is logically equivalent, meaning the only one that is true also, is the contrapositive. If not Q, then not P. And if you look back at the previous slide, you'll see that 11.4.2 is the contrapositive of 11.4.1a. The converse is not automatically true. This one is not automatically true unless the original is stated in the IFF, or if and only if form, because if you look at these two up here, they really are the original and its converse. That's only true. The converse is only true if the original is stated in the if and only if form. Otherwise, without any special stating, the original is true, the contrapositive is automatically true. All right, these should look familiar. We've had these 4 or 5 times now. They're really your computational techniques, formulas to help you find divergence. Very, very intuitive. If we look at part A, if the general expression of a series can be expressed as two separate series added together or subtracted one from the other, then the sums can be found independently by finding the sum of the first and adding the sum of the second, or subtracting depending on the original form. Part B, again, really intuitive. If C is a non-zero constant, then you can factor it out. It's really GCFing from an infinite number of added or subtracted terms. That one makes intuitive sense. And C sounds like a made-up rule, but when you think about it, it's really the divergence form of the eventually clause in sequences. So convergence or divergence is unaffected by deleting. The only caveat is a finite number of terms from a series. And then the rest of it goes sort of symbolically representing what it says in words. So really, you can knock out a finite number of terms from a series, then you get this, what would you call this one? Like the secondary series. That's the series that results from chopping off a finite number of terms from the beginning, in which case the secondary series and the first series both converge or both diverge. And that one would be useful if you don't have exactly the form that you need in the first, or the behavior, I should say, that you need in the first K terms, the first capital K terms, then just knock them out. Knock them out and look at, again, like it's the eventually analog for series as we had with sequences. So if the divergence eventually happens, then you can say that the original diverges. If convergence eventually happens, then you can say that the original converges. So that's a weird strategy, like just getting rid of the first K terms so that you can look at behavior that happens sort of now starting at capital K instead of starting at 1 and then looking at when that behavior happens eventually, because there really isn't an eventually clause for series, but it is contained in this theorem subpart. All right, as with all calculus chapters, it's like, oh, those are, 4 or 5 fun theorems. That can't be too difficult. Let's start getting into examples. I skipped example 1, very intuitive. You can look at it. I believe it was a series whose limit is 1, so you're like, okay, I got it. That one diverges. So let's look at this one, find the sum of the series. Should be intuitive that you are going to separate it according to the computational formula or theorem part that allows you to look at these things separately. So just break them apart, look at them separately. 2 over 5, k minus 1. What can we do with these? You can either keep the constant in there or take the constant out, not sure. I'm just going to start bulldozing. I'm going to take the constant out because I can. In fact, every time I do this, it winds up not being necessary, but I just like to make my general term as neat as possible. All right, now I'm going to pause and let that sink in. And by pausing to let it sink in, I mean giving me a minute to write in some stuff. Okay, we look at the left, and C is 3. That means the constant that I factored out is 3. A is 1/4. R is 1/4. Clearly a convergent geometric series. Subtract from that what's happening over there with the second one. C is 2. A is 1. R is 1/5. So we have a formula for the infinite geometric series, which is this, 1 minus R. In both cases, it's clear that they are convergent, so the sum of the left series would be 3 times, really just plug and play on that formula, 1/4 over, 3/4? Clean that up in a minute, minus 2 times, what I got, 1 over 4/5. All right, looks like the left one becomes 1 minus 5/2. What's that, 2.5? So 1 minus 2.5 should be negative 1.5, so minus 3/2. Yay, all good there. All right, what's happening here? Determine whether the following series convert. Oh, there's 2 of them. Yeah, there's part A and part B. B's on the next slide. I thought they made a Grammatical error. All right, determine whether the following series converge or diverge. The first one we're looking at is this one. I think pulling the constant, you might already see it, but pulling the constant should make it really obvious. So 5, k equals 1 to positive infinity, 1 over k. So this one diverges. And if you were asked for justification or explanation, you would say, because it is simply a constant multiplied by the divergent harmonic series. And that would be good enough for AP and me. Hey, that rhymes. All right, this one, and you're like, oh my God, well this is like a divergent harmonic series. There's nothing to write here. Well, I suppose the only thing that's different is that you're starting at 10, but this is an illustration of that last computational formula that allows you to knock out a beginning number of terms. So this one would be like, okay, diverges because deleting a finite number, forgive the abbreviation, of terms from the divergent harmonic series does not affect, wow, there's more writing than thinking on this one, affect its divergence. Wow, it's a lot of writing just to sound snooty, but yeah, that's a quick and painlessly easy example of part C. And you didn't think we would be letting the definite integral, or in fact the improper integral, go away for this chapter. We will be working with integration. So this one implies that it is called an improper integral. I think we put some of these on the AP quiz, and by we I mean me. Your intuition serves you well. You just imagine or put in a dummy variable for the top limit. The variable of choice is a capital L. I would use that instead of a lowercase l because it just looks like a 1. So a capital L, do your definite integration. It will be in terms of L, and then just send L to positive infinity. So the mechanics to that are pretty intuitive, and I think we've all seen that before. The integral test, let's read it, blah, 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 series with positive terms. So that one, there are some important hypothesis qualities, characteristics that need to be met. It is positive terms, and let f of x be the function that is in x in the general term. Got it. So you just take the general term, replace k with x, the general term then becomes a function, pop it into this improper integral form. We'll just use a different color right here and duke it out. There are some other hypotheses that have to be met. If f is decreasing and continuous on the interval a to positive infinity, so you will go back to the middle of chapter 2 to determine or to verify continuity. And then to determine decreasingness, that would be what, chapter 5. However, think some known parent functions like ln x, e to the x, things that are obvious, you can just say e to the x is increasing, blah, 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 and continuous, ln x is increasing, blah, blah, blah. Some of those are painfully obvious, but if it's not, you'll have to jump into verifying it. Continuity and tone should be obvious on how to do that. So you infer convergence or divergence of the given series from the improper integral. So the behavior of the improper integral determines the behavior of the series, which actually is cool. You could look at the series and go, I can't do anything with this based on all the series tools that we have so far. Oh, let me bring in my old friend, the integral, and go for it. All right, let's see how the integral test, plays out. This one should be the right branch of the parent rational function. So we know that it looks like this. So it's decreasing and continuous on that interval. You don't have to do anything. Maybe this little thumbnail sketch, just go, duh, I know what this thing looks like. There's no discontinuities. Things are fine. So this is 1 to L, limit L goes to positive infinity of 1 over x dx. I was wondering if I wanted to write that as x to the negative 1, but I don't because I have a known derivative form right now. So limit L approaches positive infinity. So what would this be? This would be ln x evaluated at 1 and L. So keep it going and limit it at the most convenient time. This would be what? ln L minus ln 1, which is, of course, 0. So I have limit L goes to positive infinity ln L, which equals, I know, and I hope you do too, that ln x looks like this. So that's positive infinity. Therefore, so you would say since integral diverges, so does k equals 1, positive infinity, 1 over k, done. All right, here's another integral test. Again, I don't know if I should pause and let you do it. Yeah, I'm going to do that. So I'm going to pause. Of course, it's going to seem instantaneous when you watch this. But if you want, hit pause and do it, and then I'll do it, and then it'll show up magically. All right, that's what I got for the limit. And you check my work, see if your work looks like that. Since the limit is 1, and we're really looking for the limit to exist, it really doesn't matter what the value is. So the limit exists, so you would say since integral converges, and you can say to 1 or not, your work shows it. So does k equals 1, positive infinity, 1. Hey, it's not a bad infinity considering how well, or how fast I wrote it, excuse me. All right, happy face. We looked at these last year, so there's nothing on this slide except just to look at it. I feel like letting the sound go and letting the time tick off for dramatic effect. Okay, that's just irritating. So I'm going to stop talking right now. You can look at this as long as you want. Put it in your notes. This is how everybody knows series in this form right here. I learned it as hyperharmonic. It's just cool, so if you want to sound snooty, like, ooh, we studied hyperharmonic series, not the plebeian P series. No, you can just say it with that snooty sound. It's cool. So P series look like that, and that's sort of the general form up here, how they expand. Got it. This theorem, super powerful. Just look at it. Converges if P is strictly greater than 1. Diverges if P is a what? Proper fraction all the way to 1. When P is 1, which you should see that already, when P equals 1, the P series. Oh, how funny. My phone answered me because it thought I said Siri. Well, that's irritating. All right, the P series, blah, 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 k equals 1 to positive infinity, 1 over k to the p, is the known divergent harmonic series. Got that. So again, powerful to have in your notes, powerful to recognize, could save you tons of time just by going, oh, it's a P series, and you're really looking at the exponent right here to determine convergence or divergence according to these rules. All right, this would be an example of no work to do. Well, maybe mental or physical. I'm not sure if you would manipulate the exponent physically or mentally. But I would just write it in one over k to the p form. In this case, p equals 1/3. However, I'm going to start it at k equals 2. That first term was throwing me. I'm like, how am I going to write that so that it looks exactly like a p series? But I forgot. We have the ability to simply delete a finite number of terms. So I'm going to start my justification with k equaling 2. Then I don't have to do any weird manipulation to address that first term. It's 1 over k to the p. P is 1/3. 1/3, the smaller, the proper fraction p-values are the divergent p-values. So, since 0, p, 1, this series diverges. And the last theorem of section 11.4 is this one, 11.4.6. It's buried in the proof of the integral test. We are not going to prove the integral test. You can read it if you're curious. It's interesting. It has a signed area approach to it. It's in the book. This one was buried in it. And it's really kind of a, I don't know, least upper bound kind of thing. It's like, does this m value exist? So, series of non-negative terms. If this m exists, then, for every n, and we're looking at partial series, for every n, then the series converges and the sum satisfies that. If no such m exists, then the series diverges. We don't really use this in the computational approaches for the examples that we're going to be looking at, but I thought I'd be remiss if I didn't mention it. So there, I mentioned it. But I don't think I've ever used it at all. And then this is the problem set section where there's any method. The other ones in section 11.4, the earlier problem sets, give you the specific method, which is a reasonable approach to get used to the different methods presented in this section. But of course, I like the mishmash. Like, bam, here's everything, go for it. First off, any trigonometric thing with an h right there are hyperbolic functions, an entirely new class of functions. They are addressed in our textbook before chapter 11, so within chapter 11, you sometimes might find hyperbolic functions, which would be tan h, secant h, cosine h, things like that. If you see them, skip them. If I forget to tell you not to do them, don't do them. You'll do them in Calc 2, or University Calc 2. Everything else. Like, what if we got here? Think about that. That one to me looks like you could do a quick U substitution and then have the divergent harmonic series starting at a lower value that's not 1. I'm just shooting from the hip on this one. This one looks like it would be a P series. I'm not sure. This one, I don't know, you might want to check the limit using L'Hopital. This one caught my eye, and the solutions manual just says, hey, the limit's 1, have a nice day. Don't tell you anything. I'm assuming there's a L'Hopital-ness going on for that one. I'm assuming the L'Hopital-ness goes on right here too. And that's it. This one, of course, we did not do L'Hopital forms where we had f of x to the g of x. In the L'Hopital forms, we didn't do any of those. So if you see those and they require L'Hopital, skip them. Not on the test, not on my test, not on the AP test, not at all. No, no, no. Unless this one is one of those screwball definitions for E. Sometimes they hide, and I think I had told you guys to write down all the interesting definitions of E that were earlier in the book before we left integrals and then started series. So I want to look at that one. If it is like an f of x to the g of x form that requires L'Hopitals, skip it. But I don't know, I might want to look at that one. Everything else I think looks pretty straightforward. And that's it. So if I see you tomorrow for class, I shall see you. If not, if you're celebrating Senior Ditch Day, at least you have a basis, but we will be lecturing on this tomorrow. Torre out.